There is a problem with both interrupts and signals in that they're executed in the context of the thread that was interrupted. This means that they're handled on the thread stack and can cause certain issues that will lead us to the answer of why we should sometimes disable interrupts and signals. To demonstrate this problem, let's assume we have some arbitrary thread that's executing, and this is its program counter and its stack pointer. At some point in the execution, an interrupt occurs or a signal, and as a result of that, the program counter will change and it will start pointing to the first instruction of the handler. However, notice that the stack pointer will remain the same. And in fact, this can be nested. There may be multiple interrupts or multiple signals, and in a nested fashion, they will keep executing on the stack of the thread which was interrupted. If the handling code, the handling routine, if it needs to access some state that perhaps other threads in the system would be accessing, then we have to use mutexes. However, if the thread which was interrupted already had that exact same mutex that's needed in the handling routine, we have a deadlock situation. The interrupted thread will not release the mutex until the handling routine completes the execution on its stack and returns. And we know that that clearly won't happen because this one is blocked on this mutex. To prevent from these issues, one possibility we have is to keep the handling code simple. What this means in this context is that we can prohibit the handling code to use mutexes. If there is no possibility for the handler code to block on some mutex operation, then the deadlock will not occur. The problem with this is that it's too restrictive. It limits what a handler can do. So instead of enforcing that a handler has to be simple and avoid the use of mutexes, we introduce masks. These masks allow us to dynamically enable or disable whether the handling code can interrupt the executing mutex. We call these interrupter signal masks. The mask is a sequence of bits where each bit corresponds to a specific interrupt or signal, and the value of the bit 0 or 1 will indicate whether the specific interrupter signal is disabled or enabled. When an event occurs, first the mask is checked, and if the event is enabled, then we proceed with the actual handler invocation and interrupt or signal handling. If the event is disabled, then the signal or the interrupt remains pending and it will be handled at a later time when the mask value changes. To solve the deadlock situation that we described, the thread, prior to acquiring the mutex, it would have disabled the interrupt. So then, even if the interrupt occurs, it will be disabled and it will not interrupt the execution of the thread. So it will not interrupt this critical section. If the mask indicates that an interrupt is disabled, then it will remain pending until a later time. Once the lock is freed, once we perform an unlock operation on the mutex, the thread will then reset the appropriate field in the mask. As a result, the interrupt becomes enabled, and at that point, the operating system will allow the execution of the handler code. Note that at this point, it is okay to execute this code because we no longer hold the mutex. So the thread that would be interrupted when the handler code is called doesn't hold this mutex. As a result, the deadlock will be avoided. We should point out that while an interrupt or a signal is pending, then other instances may occur and they will remain pending as well. Once the event is enabled over here, the handling routine will typically be executed only once. So if we want to ensure that a signal handling routine is executed more than once, it is not just sufficient to generate the signal more than once.